It's my pleasure to introduce Ezra Miller from Duke University, and today he'll be speaking on real multiparameter persistent homology. Thank you, Ezra.
All right, thank you. Henry, this is an odd experience for me. I don't think I've ever given a talk this way. I can see a list of names on the right, but I don't know who everybody is, and I certainly can't see anybody's face. So if something is unclear, please speak up, because there's just no other way I can detect any reaction whatsoever. Okay, so this is an outline of what I'm going to do, and these slides are listed across the top. So even though this particular slide will disappear, the list will continue. So I don't know what people's backgrounds are, and I guess I can't take a poll of how many people have seen persistent homology before, but I'll start from more or less scratch, although it'll be sort of a relatively sophisticated view of persistent homology, but starting from scratch. And then I'll go through some examples, lots of examples, a little bit of history, and then I'll get into the real content, as how one thinks about multiparameter persistent homology and what one can say about it and so on. Okay, so, collaborators, right, yeah, so this is interdisciplinary stuff, multidisciplinary stuff. So it involves biologists and mathematicians and statisticians, and the students are both math students. So there's Ashley Thomas, a grad student who's on the job market this year, and Surbi Berrywall finished her undergrad degree and might be going on a Fulbright to Guatemala, but we're not sure. She won the U.S. portion, but Guatemala still has to decide. Okay. So persistent homology, what is it? So the way I think about it, you have a topological space X, and don't worry about the word filtered by, just it has a set of subspaces, and the set is indexed by Q. And so we have X sub little q, yeah, you can see what I'm writing here. So we have XQ contained in X for all elements Q in this set Q. And the fact that these are all subsets, the fact that every X sub Q is a subset of X, means that Q is partially ordered. So just XQ is contained in XQ prime, Q is less than Q prime. And we say that this collection of subspaces has persistent homology, and that's a collection of vector spaces, H sub Q, and it's indexed, so H sub Q such that Q is in Q, and it's just the homology of XQ with coefficients in K. Now, I'm sort of both going to assume that you've seen homology before and not really care for the most part that you've seen homology before, because what's really important was that we have a collection of vector spaces indexed by this partially ordered set Q. That's really all that's important for the moment. But I'll give examples to indicate what the topology feels like. So this persistent homology is a Q module over the poset Q. So what I mean is it's a family of vector spaces over this fixed field K. Doesn't really matter to me what this field is. You can think of it as the reals or complexes, or if you're computational, think of it as F2, the field of two elements. Really doesn't matter to me. And you have a homomorphism, HQ to HQ prime, whenever Q precedes Q prime in the poset. And we want one extra condition, and that is basically a commutative condition, or a transitivity condition, if you like. It says that the map from HQ to HQ double prime, you can go through any Q prime in the middle, and it doesn't matter which one. The point is that if you have HQ and HQ double prime, the map from HQ to HQ double prime is the same. It just comes from the inclusion from XQ into XQ double prime. And it doesn't matter if you include XQ into XQ prime first, and then XQ prime into XQ double prime. The map on homology is functorial, so it doesn't matter. This observation means that we're really doing commutative algebra rather than just arbitrary representations of quivers. Okay, so some examples. Again, ask questions if you have them. I can't see anybody's reaction to this. I don't know whether everybody's glazing over or anything, but just ask questions if you have them. So examples, points in Rn. So this is the standard, usual one parameter persistence. So I'm thinking this is my topological space, and this is a collection of points, and I'm just going to take an increasing collection of disks. There are 31 of these disks. And then you start expanding them. There's still 31, now there's 26. And the map on homology sends the basis vector for this one and the basis vector for this one. It sends them both to the basis vector for this connected component. That's the map on homology. So that's the persistent homology there. And then you keep expanding the balls, and the homology changes. It goes down, and and then you get H1s. So there's a loop over here, and there's a big loop over here. And this loop is more persistent than this loop because this loop disappears after a little bit, and this big loop persists for a while. In the meantime, an extra loop gets created here, an extra loop gets created, is born there, and then both of those die, but this one still persists. And you keep going, and one more loop will be created up here. Yeah, there it is, and then it disappears. Okay, so that's the usual view of one parameter persistence. And you can view the partially ordered set. You can view it as that set of 0 through m. So I press the space bar a few times, and you can view that as the partially ordered set, or you can view it as the real numbers. So view the parameters varying only one parameter for the moment, varying continuously. Here's another example of one parameter persistence. This is a little bit, this is kind of the standard, another standard view. It's the sort of the sub-level set view of persistence. So here's Steve Marin's brain, and this is actually the arteries in Steve Marin's brain, and we're going to start filling it with blood, but not in the usual way. We're just going to lift a plane from the bottom to the top and take all the points beneath that plane. So now we have 6 connected components, and then you lift it a little bit, and some of the connected components join, and some new ones are born, and then you keep going this way until the whole thing is full. And what you do is you track those connected components. Whoops! You track those connected components as the plane goes up. Okay, wing vane. So this is going to, and again, as with the other case, you can view it as either a discrete set of the parameters, either a discrete set 0 through m, or you can view it as continuous parameters. The point being that at only finitely many parameters does anything change. So there's some parameters where some connected components join, some where they're born, but most of the time when you move a little bit of epsilon, the connected components get a little bit bigger, but they don't actually, new ones are formed and no connected components join. Okay, so here's a 2-parameter example. These are fly wings. So these are 3 normal Drosophila melanogaster fly wings. And you're not supposed to be able to tell the difference between these. They are different, but they look pretty much the same, and that's kind of the point. The variation in these things, they can get wider and longer, and these intersection points can move a little bit and so on. But the topology of the graph stays the same. These are abnormal veins, abnormal wings. So usually I do interactive things where I ask if anyone sees what the differences are, but since this is a weird format, I won't do that because I can't even see if you're raising your hand. So I'll just point out that this one has an extra wiggle, this one has some extra wiggles, this one has an extra bar over here, this one has another extra bar, but it's at a different level. This one, the connection doesn't actually form, and this one has a little extra sort of triangle up there. So these are topologically abnormal wings, abnormal veins in fly wings. Here's a close-up photographic image. You'll notice that this one is an extra bar, but it's questionable whether it actually reaches this vein over here. So this longitudinal vein might not actually meet this extra cross vein. Oh well. So we asked the biologists whether or not it does. But for the moment, what the biologists give us is this, and this is a spline that they fit to the wing. Now you'll notice that there was an extra cross vein there. Oops, sorry, over there, and they completely ignore it. They purposely ignore it to say, well, that's an abnormal feature, and we're just gonna make our program to just ignore those abnormal features. So the study that we want to do is to actually mark up the abnormal ones, and then do a study where we include the abnormal ones in the variation that we're trying to study. The problem is, of course, that you have then planar graphs with varying topology, and people don't have methods to do analysis on data sets like that. So the hypothesis is, okay, so this is what we're actually trying to test in our biological investigation, is when does this topological novelty arise? And the idea is that it should arise when you do a continuous selection experiment. So this is not what they do, but let's suppose that they did, just for example, if they did an experiment where they mated some flies and picked the offspring with the longest wings, and then they mated those and they picked the offspring with the longest wings. Lo and behold, you observe that the offspring tend to have longer wings when you do that, but they also tend to have much higher rates of this topological variation. And the hypothesis is that when you directionally select like that, it pushes the developmental program, that is how the wing develops. It starts with a disc and then it folds in half, and then there are protein gradients and so on. It pushes that program beyond a threshold, and when you push that program beyond a threshold, you get new topological variants. That's the hypothesis that we're trying to test. I can go into more detail about that, but I'd rather just tell you how we use persistence to summarize these wings. So
Ezra,
what we're going to do is,
quick question. In the fly wings, when the biologists make those splines, do they draw the splines by hand, or do they mark points by hand and then have a computer fill it in, or how do they make their splines?
So they used to mark points by hand. I think they now use an automated system that marks the points and finds out where the points are, and then it fits the splines. So they have software to do it now.
Uh-huh.
They used to do it by hand, but now they have software. And these splines are a bunch of quadratic curves, quadratic Bezier curves joined together at various points. But it might be that the vertices are marked by hand. In any case, we need the biologist to mark these vertices by hand, because we know that those aren't going to be marked by computer. Right. We don't want to do that as mathematicians. We want the biologists to mark those points. So that's where the data set sits at the moment. It sits with the biologists so they can mark up these weird topologies. Okay, let's see. So how do we encode these fly wings? So we're going to use two parameters. The first parameter is going to be the distance from the vertex set in the usual way. So these are just points in R2. So we're just going to expand those. That's the usual thing that you're used to seeing. And then with the second parameter is going to be the distance from the edge set. These are given as Bezier curves, and we're going to expand those. But now we're going to look at, so we're going to require the distance to be greater than or equal to minus r. Why the minus sign? It's because, you'll see in a second, the sublevel set is going to be near the edges but far from the vertices. So we want to take the union of the stuff that is red but not blue. So we're removing the blue stuff from the topological space. That means that when we make R in a real number sense get bigger, we need to have a bigger topological space. So that means, but when we make R get bigger, we're making the radius, we have to make the radius decrease. So that's why we take minus R. So think of R as the radius, and you take, when minus R gets bigger, the radius is actually decreasing, and that's giving you more red stuff, so it's giving you a bigger topological space. This is where it would be very useful to see your faces, if that's making any sense. But the point is, when you shrink the disks, you get a bigger topological space. That's going to the from your point of view, let's see, to the right. And when you thicken the edges, you're making the S parameter get up, and that go higher, and that's going up. And the point is that when you go this way or that way, you are getting a bigger topological space, and that's what persistence is supposed to tell you. So the multi-scale summary says that you take this WRS, that's the stuff that's red but not blue, and you take the homology of that. You could be looking at the connected components, you could be looking at the loops, depending on whether you take H0 or H1. And what you end up with is a Z2 module. If you think you start with the homology when you have a fixed radius and a fixed thickness, you can think S stands for semi-thickness if you want. So R and S is radius and semi-thickness. When you have fixed radius and semi-thickness, when you make R go up, which is actually making the radius get smaller, you're getting a bigger topological space. You get a map on homology that goes this way. When you let the semi-thickness go up, then you are getting more red stuff, thicker veins, and that's giving you a bigger topological space, so you get a map on homology that goes this way. And that's the point. So you can just click, go, R minus epsilon goes to R plus epsilon, and S minus delta goes to S plus delta. You get this array, this diagram of homology vector spaces, indexed by here Z2, if you discretized. But see, the thing is, you didn't actually need to discretize. You could have just used R2 instead, but then you just have real two-parameter persistence instead of integer two-parameter persistence. Okay, so here is another example. This is a standard example that was actually in the very first paper on multiparameter persistence in 2009 by Carlson and Zomerodian, but I'll give somewhat a detailed explanation because it's one of the motivations for what we're doing here. And this one, you really do want to use two continuous parameters, not really two discrete or continuous parameters. So here we have topology of probability distributions. So suppose you have a measure on a space. You should think of M as being R to the D, and mu is some nice measure that comes from, let's say, well, you can make it a smooth one, or you can take it singular but support it on like a circle or something. Take a kernel function of bandwidth R. So what I mean is take KR to be Gaussian, for instance. variance r, or maybe a uniform measure on a ball of radius r, and we're going to now convolve with kr, and that's going to expand the measure in some kind of way. So, for example, if you take an n-point sample from your measure mu, right? So mu n is uniform on an n-point sample from mu, then you can expand that measure. So this is now just a finite set of points. And when you expand it, you're going to get sort of a sum of disks or a sum of Gaussians, and that's going to approximate this expansion of mu. So here's what the picture looks like. So if your original measure mu was uniform on a circle, just a circle, not the disk, but a circle, so it's a singular measure, then when you sample n points, and then you hang a Gaussian off of each of them, when you add those up, you get this sort of volcano-like thing where it's not quite a smooth, it's not a flat volcano. The original distribution, when you convolve with the Gaussian, you're going to get something that's the volcano where it has literally a flat circle on top, and then it kind of decays away from that flat circle. When you sample from it, then you're going to get this sort of bumpy rim to the volcano over here. If you had a non-uniform distribution on the circle, let's say it was really high at one end and really low at one end, the other end, then when you convolve with the Gaussian, you're going to end up with this sort of I don't know, tilted fedora-like picture, very tilted, where it's higher at one end and lower at the other end. Both of these distributions are, of course, supported on the entire plane. So, but they're sort of their highest density is in this case near the circle, and in this case sort of near the circle, but sort of higher on one end than the other. Okay, so if you convolve with a measure that has a density, then you do the usual formula. This is a formula that some of you have seen, so I'll just leave it there. So in general, if you have a measure with a density function f, then I want to define its support at sensitivity s. So the point is, in that previous picture, we had distributions where there was density, non-zero density everywhere on the entire plane, but that doesn't really describe what we're looking at. So what we want to do is have some sensitivity, and let's look at the set of points in the space where the density is at least 1 over s. Now, why 1 over s is so that when sensitivity goes up, you get a bigger topological space. Right, so so what you're doing is you're looking at the set of points in those pictures where the height is above a certain level. So when I let the level go down, the set of points that I'm looking at gets bigger. That's the reason to take the 1 over s thing there. So then the expansion of mu to bandwidth r and sensitivity s, what you do is you expand it to bandwidth r. That's the sort of fattening, smoothing-like thing to do, and then you threshold at this r to the d times s. So why r to the d times s? Because that makes it so that let me say what's going on here. Let's just look at the picture first. So when you threshold this, so this is an expansion to bandwidth r, and then when we take a sensitivity s, what we're doing is we're thresholding at some level, and the point is that that for many values of that thresholding level, what the topology of the set you're going to look at, it's going to be an annulus. And that topology is reflecting the support of the original measure you were sampling from, which remember was a circle. So the idea is to learn somehow that there was a circular shaped thing there, and then the way to learn that is to expand and then threshold so that you get some idea of what the geometry of that support looks like. Here, when you threshold, most of the time you're going to get a crescent, and that crescent is going to have no topology in any way. It's just going to be some crescent, but that crescent is a reflection of what the measure kind of looked like originally. And when you get low enough, you'll get sort of a full circle, but not for very long before you get down to 0, and then you get the whole plane. Okay, so the expansion to bandwidth r and sensitivity s is this: you expand to bandwidth r, and then you threshold at this number r to the d times s. And the point is that these Vr mu r to the d times s, these are nested as r and s increase. That's what the r to the d times s does. It makes it so that it's nested. The idea is that if you had a bunch of points and you put disks, you put balls around them, then when you put fatter balls, you have to lower the heights of those disks. So remember, each of these points is really a delta function. And when you put a ball around it, it's going to be a disk, but the disk is going to be at some height. It's really a cylinder. And when you widen the cylinder, you have to lower the top of the cylinder, and that's why you have to do r to the d times s, so they don't lower below the threshold and so on. So what topological data analysis does is, instead of looking at the actual set, it looks at the homology of the set. of this expansion bandwidth, the homology of the expansion. So the ith bipersistent homology, you look at all of these vector spaces for all choice of bandwidth and sensitivity, and this is an invariant of your measure. And given this is an invariant of your measure, the algebra and the geometry and the combinatorics of this biparameter persistent homology module is intimately tied to the statistics of sampling from the measure nu. Oops, that should have said mu, I think. Yeah, that should have, well, okay, it doesn't matter. I'm sort of technically correct, but both of these should have been mu's, I think. In any case, this algebra, geometry, and combinatorics in this talk is going to correspond to presentation, that's the algebra. Geometry, that's primary decomposition, and combinatorics, that's finite encoding. Okay, questions about that? That's kind of a standard picture. And just a couple of comments. If you take the poset to be z to the n, then the module H is a z to the n graded module over the polynomial ring in n variables. That's the same thing. It's not just an equivalence of categories or something like that. A z to the n module is the same thing as a z to the n graded module over the polynomial ring in x1 through xn. When you move up in the ith direction, that's multiplication by xi. And similarly, that's standard commutative algebra. And similarly, if you take Q to be Rn, then you're going to get an Rn graded module over this funny ring, where the funny ring is like polynomials. It is polynomials, except that the exponents are allowed to be real instead of integer. So it's like a real exponent polynomial ring, right? This is just to say that if you want to be thinking about this in terms of commutative algebra, you can. We won't exactly. We'll be taking sort of some hints from commutative algebra, but we'll be thinking them in terms of sort of more combinatorics and modules over posets and these kinds of things. Oh yeah, right. I had a comment to make here. So in the usual TDA sort of paradigm, there's what's different here is that these dots are changing colors. There's two ways of using persistent homology here. So for the points in Rn and for the probability distributions, what we're really doing is we're summarizing a data set. So you think that probability distribution, really you have a large sample from a probability distribution. You want to summarize somehow the distribution that you're sampling from. That's summarizing a data set or a population. Same with the points in Rn. In contrast, the brain arteries and the wings, we're summarizing data objects. And when you summarize data objects, you get one persistence object, one persistence module for each data point, not for each data set. So here you get the yellow ones give you one persistence diagram for each data set. The green ones give you one persistence diagram for each data point. That's just to point out that there's a difference in how persistence is being used. Okay, so some history. I'm going to do this briefly. It traces back to Morse in the 40s. If you think about what Morse theory is, it's really sort of sub-level set persistence, and you're kind of tracking the homology as you raise the threshold or lower the threshold, however you want to view it. Dink and Quivers have finite representation type. So this is a precursor to the statement that that ordinary persistence modules have barcodes. That statement was made precise, contrary to the thinking in the TDA community. It was made precise in 1980. If you look at this paper by Abiasis and Delfra, they write down, they're talking about representations of the type A quiver. So that's just, sequences of vector space maps. And they have pictures that are visibly barcodes. They have, they write down one of these modules, and then they have a sequence of boxes here, and a sequence of boxes there, and a sequence of boxes there, and a sequence of boxes. It is a barcode, and they call it a diagram. Ordinary one parameter persistence in the sort of topological sense was made precise in these two papers in 1999. One of them really did, this is really persistent homotopy, but let's, close enough. And then the efficient computation was started to be introduced in 2002. And multiparameter persistence, which was introduced in 2009. Now, for multiparameter persistence, the rest of the slide is all about multiparameter persistence. There's been a lot of work on it. There's algorithms and presentations and visualizations and notions of noise, and this involves a lot of people. But almost all of these papers assume that the modules are finitely presented, and they use z to the n, they use z to the d, z to the n. And they apply standard combinatorial commutative algebra. This is not to say that what they're doing is already standard combinatorial commutative algebra. It's just to say that the context in which they're working is a context in which standard combinatorial commutative algebra applies. Now, there are mentions of real multi-parameter persistence in some of these papers. Even in the original one, they say that you should use R to the n, but then all of their results, without further comment, they don't actually say, okay, but now we're going to do everything over z to the n, but they do. They immediately restrict to z to the n, the discrete case. And the same thing, there are papers that mention, oh, look, here's a real example, but let's do all of our theory in the z to the n case because we don't know how to do the real case. So this talk will be about the real case, and that's kind of the point. Now, for metrics, that is, when you're doing statistics with persistence diagrams, you have to know how far apart persistence diagrams are, and for that, you need a metric or a pseudo-metric on persistence diagrams, and there is no discreteness hypothesis there. So Lesnick's paper from 2011, where he does interleaving distance, he assumes that the modules are R to the n modules. And this rank function stability, which is a very cool observation, that when you take functions, when you take sub-level sets of functions, sort of multi-parameter sub-level sets of functions, real functions, that when you that the homology of the sub-level set might be really bad, but when you look at the rank of the homology as it maps from one parameter to another parameter, somehow the map tames the badness because of the say the continuity of the function that you're taking the sub-level sets of. So it's a very cool observation that ranks are stable even if the homology itself is not so stable. Okay, so structure theory, there's not that much that's been done previously. So you can restrict to parameter lines, so lines in the parameter space, and that gives you lots of one-parameter modules, and then we can understand their barcodes. When the modules are finitely presented, there's a Krull-Schmidt theorem. They're direct sums of indecomposables. When if you have discretely generated ideals in this sort of real exponent polynomial ring, then you can basically the algebra is the same as it is for the integer exponents, because you have a discrete set of exponents, and then all that matters really is the partially ordered set of them. And you can also try to apply non-commutative quiver representation theory. This kind of works in the z to the n setting, and it just fails miserably in the r to the n setting, because the quivers are very far from locally finite. If you look at any point in Rn, you look at its neighbors, well, it has uncountably many neighbors. Just sort of take a circle, a little circular arc around it, and then look at all the points between your point and that circle, and there's sort of one in each direction. So it's really very, very infinite, which makes all these nice algebraic theories not work so well. Questions about the history?
I had a question, Ezra. Could you briefly say what rank function stability is again, roughly?
So you can look at, so instead of looking at just the dimensions, let's look at the dimensions of the, if you have a multi-parameter persistence module, then you can look at the dimension of the vector space at every parameter. And when you have a continuous, say it again?
That might be infinite.
That's the Hilbert function. So if you're looking at continuous functions, then let's just suppose that that's finite.
I see.
You can have infinite even for continuous functions, that's true. But okay, let's suppose that it's infinite. It doesn't really matter to me. It doesn't really matter to them, actually, that it's infinite. The point is that while the dimensions themselves may be infinite, the ranks of the maps that go from one point to another point, those things should be finite.
Okay.
And stable in the appropriate sense. So the rank function is not the Hilbert function, it's the rank of the map from the vector space here to the vector space there. And those things with not very much hypothesis on the function that you're taking the sub-level sets of, those things are stable and finite.
Got it.
Even though the dimensions of the vector spaces might be really bad because there's a huge amount of noise, when you sort of go macroscopic distance away from this parameter to another parameter, that noise goes away, and all you're looking at is a sort of classes that persist for some amount of time. That's stable, is what they're doing.
Thanks.
Yeah. So let's look at a toy model, the fly wings. So here's a piece of fly wing vane, and you should think of this not as a point and three lines, but as a disk and three sort of infinite rectangle rays. They're thick; they actually have thickness. And when you have this picture, you end up getting, well, there's either going to be three connected components or one connected component. In this picture, you end up either with, let's see now, what's this? This is when the radius is sufficiently big that it eats into all three pieces, then you end up with three connected components. That's the yellow region over here. right? That says that the radius is bigger than the thickness, is sufficiently bigger than the thickness. And then this one over here is when the radius is, fairly small and the thickness is fairly small, then you can end up getting exactly two connected components. That's the picture that we've drawn, in fact, over here. Notice if the disk got bigger, then it would separate this into two pieces, and so you'd get three connected components. And if you thickened the red stuff too much, then you'd swallow the disk, and then you get only one connected component. So this is the region of R and S, radius and thickness, that give you three connected components. This is the region that gives you two connected components. This is the region that gives you one connected component. And really what I've drawn here is not the module itself, but the Hilbert function of the module. It's three over here, two over here, and one over here. And just for Henry's question, the rank of the map would go from, if you look at the map from here, from the vector spaces here to the vector spaces here, then it's a rank 2 map because it takes a three-dimensional thing surjectively onto a two-dimensional thing. Okay. So the observation, if you stratify differently, though, you're getting different answers, right? So here you're getting two regions. So when you separate this guy, now you're getting three regions. But if instead of putting the point over here, if we put it over here, if we actually removed it, then we'd get something that doesn't depend on the radius at all. So it's just sort of a product of this ray with something that's got two connected components and then one connected component as soon as the red is thick enough. Or we could put it over here, and then we get this different persistence module, or we could put something on both, and we get this one. Notice these things have different hyperbolic arcs there. And then we could do this picture, which I think is the most interesting. But which stratification we use for the wings is dependent on how the analysis works. So we'll have to decide that later. Although actually I find this one kind of unlikely, because we're not supposed to know where that intersection point actually is. That's not really there in the wing. In any case, we'll have to choose. So the observations, there's only finitely many regions. The stratification alters the persistence module. That's a good thing, because the whole point was to sort of highlight the intersection points. And that the discrete approximates algebraic. So here's the picture. We could have taken, instead of using real parameters, we could have used discrete parameters, and we would have gotten a picture that looks like this. And I claim that this is not a good thing to do for a couple of reasons. First of all, you'd have to choose a step size. When you choose a step size, you then have to actually compute these things, and then you have to store all this information about where it was yellow, where it was green, and where it was, or olive colored, I guess, and where it was blue. But how are you going to store this set of lattice points? Well, as you remember, this is just a two-dimensional example, but in general, you could have an n-dimensional example, and you have to store a whole bunch of lattice points, and the number of them is exponential, in the dimension anyway, in the number of parameters. But what is this set of lattice points? This is the set of lattice points that is above, but as close as possible to this algebraic curve. And if you're going to remember that this set of points is the set of points that are above, but as close as possible to this algebraic curve, why not just remember this algebraic curve and say all the points above this all the points below this algebraic curve are yellow, and all the points above the algebraic curve are something else. And then for the green, for these points over here, you say that all the points between this algebraic curve and that algebraic curve are this green, and everything above this algebraic curve, those things are blue. If you're going to remember the algebraic curve anyway, you may as well only remember the algebraic curve and not bother remembering the discrete set of points that you happened to randomly choose above those algebraic curves. It's better for computation, and it's better theoretically anyway. Okay. And also, right, taking a discrete set doesn't guarantee that the module is finitely generated, because these points march off to infinity in this direction. And so there's infinitely many generators of this module anyway. So it doesn't even help you get into a situation where you're working with noetherian commutative algebra. So it really just hasn't helped you. So, and in fact, what that raises is that we should be thinking about what finiteness condition should we use. So for z to the n modules, remember those are modules over a polynomial ring in n variables. There's such a thing as a noetherian module. And all finitely generated modules are noetherian, and this is why everyone makes the assumption in their papers on multiparameter persistence that the module is finitely presented or finitely generated over a polynomial ring, because then you have all of commutative algebra to help you. But for Rn modules from data analysis, that just isn't going to work. They're not noetherian at all. I mean, this example over here has, let's say, a relation along each of the points on this closed on this real ray. So there's uncountably many relations that occur over here. It's just not amenable to being noetherian at all. So let's try to define some sort of finiteness condition. So I'm going to define our module, persistence module H, to admit a constant subdivision if it's partitioned, if the poset, and you should think of the poset here as being R to the n. It works. This works for any poset, but think of Q as being R to the n because it's a geometric version, geometric picture. So it has constant regions A, and so for each constant region, you're going to get a vector space, one vector space for the entire region, and you want that vector space to be isomorphic to the vector spaces for the points in that region. And you want there to be no monodromy. So if you take any A in one region and B in another region, and you look at the map from HA to H, from H little a to H little b, then that's going to induce a map from H capital A to H little a to H little b to H capital B, where really this arrow is the inverse of the isomorphism that goes from capital B to little b. And I want that the map from H capital A to H capital B doesn't depend on which little a and little b you use to represent it. So the picture here is like this. This is the same picture you just saw, but now I'm going to do this. So there's one vector space for all these yellow points, and that's a k cubed. And there's one vector space for all these green points, that's k squared. And there's one vector space for all these blue points, that's just k. And the map from k cubed to k squared doesn't matter if I chose this point mapping to this one, or this point mapping to this one, or this point mapping to that one. The map from this K3 to the K2 is the same no matter which yellow point you choose and which green point you choose. That's the no monodromy condition. And we're going to declare the module to be tame if the vector space dimensions are all finite and it admits a finite constant subdivision. So here's another example. If we take a vector space sitting at the origin in R2 of dimension 1. So we're going to have one-dimensional vector space sitting at the origin, and we're going to cover the entire plane with one-dimensional vector spaces, and then take the direct sum. We get this module over here that's got rank 1 everywhere except at the origin where it has rank 2, and it's constant. You can take constant regions consisting of this point and the complement of that point. Those are the constant regions. Note that the map from the vector space over here to the vector space over here is an isomorphism from K to K, even though you could go from K to K2 into K, right? K to K squared to K. The induced map from K to K is still just the identity map. Okay, here's another example. We can fix a poset and we can look at any upset or any downset. You can try to read this, but don't bother. The picture is much easier. An upset is closed under going up. So you have this blue curve and everything above the blue curve is in there. And a downset is closed under going down. So as soon as you have a point in there, you have everything beneath it. And so this is closed under going down. Here's a three-dimensional example that comes from a paper by Okunkov. This is a continuous upset, and this is a discrete downset. And the point is that somehow that the limit, this guy is the limit of these guys as the discrete parameter goes to 0, as the sort of the epsilon goes to 0, the step size goes to 0. And for any subset of our poset, we can define this this K of S. That's going to be put a one-dimensional vector space everywhere on S. So, for instance, here we'd view this as a module over the poset by putting one-dimensional vector spaces everywhere in this blue region and zero-dimensional vector spaces everywhere in the white region. And here we can put one-dimensional vector spaces everywhere in the red region, and here we put zero-dimensional. We just put 0. So the map from here to here is the 0 map. The map from here to here, that's also the 0 map, although this one's the map from 0 into something, and this is a map from something to 0. So these are different, they're sort of a different nature, but still you can just put one-dimensional vector spaces everywhere. Okay. So what's a bar? So a lot of you have probably seen one-parameter persistence before, and you're used to seeing what a bar code is. So let me talk about what a bar is. When you do ordinary one-parameter persistence, when you take a bar, take a half-open interval, let's say. In fact, it's half-open. It's not really relevant, but I did it for illustration. Take a half-open interval and you put one-dimensional vector spaces there. What you get is either a quotient or it's an image of a map. So let me draw pictures because that's going to make it clearer. If you take a ray that starts at A and goes off to infinity to the right like this, you take a ray that starts at B and goes off to infinity to the right like this, then first of all, this ray that starts at B is a submodule of the ray that starts at A. It's just everything in here that's got a one-dimensional vector space from B onward, and it's got 0 between here and here, but it's still a submodule of this guy. You just have 0, 0, 0, 0, 0, and then you start having one dimensions here. So this one is a submodule of this one, and the quotient has one-dimensional vector spaces everywhere from starting at A and ending right before B. You could also say, suppose you take a left-pointing ray that ends just before B, so has an open right endpoint at B, and you look at the submodule of that that starts at A, then what you get is the interval from A to B with B not included because the right-hand endpoint of this ray was open. Are there questions about this picture? Because this picture is kind of a fundamental view of what is a bar in one-parameter persistence. Okay, so this is an upset presentation, and this is called a fringe presentation. This guy is new from commutative algebra. People don't usually present modules this way. This one is sort of new from commutative algebra. The analog of an upset presentation is really a free presentation. And in this case, these modules are in fact both free because it's in the one-parameter case. Once you get into the two-parameter case, it begins to look very different. So note that A equals minus infinity and B equals plus infinity are both allowed. There's no reason why you can't have a bar that extends infinitely to the right, sorry, to the left, or a bar that extends infinitely to the right. Those are perfectly allowed. Although when A is minus infinity, then you have to have an open left endpoint there because you don't really want to include the minus infinity there. Okay, so in Rn for n at least 2, a bar is an interval. And then you get the same thing. It's either a quotient module or it's the image of a module from an upset to a downset. Notice in this picture, these are both upsets, whereas this guy, this blue one is an upset, but this red one is a downset. So we can do the same thing in R2. So now what we have is we have this upset, everything that's strictly above this red dotted curve, that's an upset. And we have, and I claim that it's a sub-upset of this one. So remember, that's because the red curve sits above the blue curve. So all this blue stuff sits inside of all this blue stuff, and the co-kernel is the stuff that's between the red and the blue over here. And here, this blue stuff maps to the red stuff, but all of the blue stuff that sits above this red curve has to go to 0, and all the red stuff that sits below this blue curve doesn't get hit, so the image is exactly this same module. So this is just a two-dimensional version of what we used in the one-dimensional case over here. Questions about that? Okay.
I had a question, Ezra. So in 1D, the anything you can represent with the upset presentation, you can also do with the fringe. Is that also the case in higher dimensions, that anything you can represent in one representation, you can do both, for the fringe, the other one, and vice versa?
The answer is yes, and we will get there.
Okay, cool.
Good. That's exactly the point, one of the points. Okay, so what's a bar code? In ordinary n equals 1, that's ordinary persistence with one parameter. Your module is always a direct sum of bars. So it's a direct sum of, remember this ij, that's an interval. And so you're going to take a k of that interval, so that's a one-dimensional vector space on that interval, and that's going to be direct sum of either these upset presentations of bars or fringe presentations of bars. And in algebraic language, what I'd like to say is that there's a map from this, so in the fringe case, let's just say, there's a map from this upset to that downset, this upset to that downset, this upset to that downset, and the map is just the usual. It just takes it's not inclusion exactly. It's sort of a quotient and an inclusion. Because this one is really a submodule of this one. Anyway. But the point is it's diagonalizable, is that this one is paired with that one. This left endpoint, think of this as a left endpoint, think of that as a right endpoint. Think of this as a left endpoint, think of that as a right endpoint. So in for the higher dimensional case, you have to do something slightly different. So an Rn module is finitely encoded if it has either an upset presentation, which is going to be a homomorphism from a direct sum of these upsets to a direct sum of upsets, and you want the co-kernel to be H, or you want it to have a fringe presentation, which is going to be a homomorphism from a direct sum of upsets to a direct sum of downsets, and you want the image to be H. So you should, this notion kind of sort of appears in previous papers there's one by Carlson, Singh, and Homology, where they're kind of looking at the set of parameters where a face of a simplicial complex appears. That's generally an upset and not just a free module. If you in the what they call the one something case, the one essential, I don't remember what it's called, case, then that's the one where the modules are free and not just upsets. So notice the difference between a barcode and an encoding is that in a barcode, you're taking a direct sum of co-kernels or a direct sum of images. Whereas in encoding, you're taking a co-kernel of a direct sum, a map of direct sums, or the image of a map of direct sums. So you've switched the order of taking the co-kernels and the direct sums. What that means is that you have a monomial, you have this matrix here where you have a list of upsets and a list of downsets, and the whole matrix is allowed to be non-zero. It doesn't decompose as there's one upset, one downset, and you put a one coefficient there, and all the rest are zero. It's that there's arbitrary coefficients in here. So these are the birth upsets, these are death downsets, and these things are called scalar entries. Why I call them birth upsets? Because if you think about what the topology is saying, the classes are born along the lower boundaries of these upsets, and they die along the upper boundaries of these downsets. So there's births. That's what a left endpoint is a birth. The lower boundary of an upset is a collection of births. The right endpoint is a death. So that means the upper boundary of a downset would be a collection of deaths. And the point is there's lots of ways to die. So if you have one birth, there's still lots of ways to die. So this represents this algebraic information, but this guy over here, this is something you can put in the computer, because these U's and D's, they have boundaries that are algebraic curves, and these are just scalars inside your field K. So this is a perfect good data structure for computation. And that's kind of the point. Well, really the point is this, that a Q-finite module, so Q-finite means that all the vector spaces have finite dimension, and this module is finitely encoded if and only if it admits one, and hence all of the following. So this is Henry's question, exactly, but plus a whole bunch more. It contains Henry's question, let's say. So a finite constant subdivision that says that H is tame. So finitely encoded is the same as tame. So that's the same thing as having a finite fringe or finite upset presentation. That's by definition. Of course, the fact that these two things are equivalent is part of the theorem. Having finite fringe and finite upset presentation it's a theorem that those things are equivalent. It's the same thing as having a finite downset co-presentation. That's the same as an upset presentation, but with the arrows reversed. A finite upset resolution that says you can keep going and not just take an upset presentation, but keep going. And what you want is that the resolution stops at a certain point. That's what it means to be a finite upset resolution, and having a finite downset resolution. So this is really the sort of the Hilbert-Syzygy theorem for R to the n graded modules over this real exponent polynomial ring. So we're not talking about free presentations, we're talking about upset presentations. Free presentations probably follows from this, although I haven't thought about that. Because I don't really care. I don't want to use a free presentation of a module over Rn, because a free presentation of a module over Rn will have uncountably many generators and worse uncountably many relations. It's just not the right thing to do. You want a nice finite data structure. So the homological algebra of multiparameter persistence modules reduces to homological algebra of upsets and downsets, and that's something that we actually can think about geometrically and can get our hands on. So there's more commutative algebra if you take Q. So this is over an arbitrary poset. This has nothing to do with Rn or Z to the n. When you take Q to be Zn or Rn, then you end up with this notion of minimal generator and minimal cogenerator, which is the same as a Sakho element, and you have minimal primary decomposition. And just as a note, these things work. Primary decomposition works over any polyhedral partially ordered group, which is Rn or Zn or really any real, totally ordered group with a positive cone that is polyhedral, that has only finitely many facets. That's what this, or finitely many faces, let's say. That's just a comment, but you should think of Zn or Rn with the standard partial order on it. Now, I know I'm basically out of time, so I just want to go through just a little bit of geometry so you can see what this stuff looks like. This is what a typical sort of Rn module would look like, and you can have a closed death if it's along this curve, or you can have an open birth if it's at this point, because the point is not actually there, but you can take a birth there, and then you can have an open death, and the point is there's some shape to this death or birth, and that shape is a simplicial subcomplex. I won't get into exactly why that is, but basically there's some faces of the cone that are there and some faces of the cone that are missing, and you can't have like half of a face of the cone. Every face is either there or not there. And that's the face being 0, that's the face being the x-axis. You can also have deaths along an axis like this. You can have a birth along an axis like this. So this happens in the one parameter case too. You can have infinite bars. It's just that in 2 parameters, you can be infinite in this direction, or you can be infinite in this direction, or any combination of those things. These types of deaths or births, those correspond to faces of this cone, this Rn plus. Okay, and decomposition, there's a notion of coprimary. Briefly, an element is coprimary if it persists in some directions and dies eventually in all of the other directions. So these are the elements. So in this module, these are the elements that are zero coprimary. That is, ooh, that's the wrong picture actually. This line should be up here. Actually, should be right at the bottom, right there. So this horizontal line should be up, sort of this distance. It shouldn't go down to the axis. It should go down only to here. This one, these are these are coprimary elements. These are coprimary elements, and this guy is the union of these three that corresponds to a minimal primary decomposition that looks like this. And you'll note that this one is missing because it's actually redundant. And these decompositions are canonical when you take a downset, which this thing is. This is a downset, and so this decomposition is canonical, as is this one actually, but sort of for different reasons, for different kinds of different universes. This one is canonical for any polyhedral partially ordered group. This one is canonical in the real or integer case, and when you know what minimal means. And the proof is you have to develop commutative algebra over this non-noetherian ring, and it's a pain. And genuinely weird things happen, like this redundant component, which does not happen in the z to the n usual noetherian case. To go from here, well, there's the biology. We're going to test this topological novelty hypothesis, and that means we have to mark up the wings with weird topology and then analyze these biparameter persistence summaries. Right now, the project sits at this stage. The wings are being marked up with weird topology. Commutative algebra, we need to know about distances between modules. I talked about that a little bit. This via K-theory, what that says is we really want to use primary decomposition to take the distances between, say, if you have a module that looks like this, you want to look at its points with support at the origin, points supported along the x-axis, points supported along the y-axis, and then if you have a pair of modules, you compare these components, then compare these components, and compare those components. Or to do this kind of thing, but in a rather non-canonical kind of way. There's also, just as a commutative algebra thing, the minimal resolution length in the Syzygy theorem. I don't actually know what that length is, whether N is abound, for instance. If you're looking at Rn modules, I don't know that N is abound. It should be, but I don't actually have a proof of that. Computation, we need to be able to compute with fringe presentations and these nice these data structures that we have, these monomial matrices. We need to be able to compute with those things. So that means we probably have to do some sort of real algebraic geometry with the upsets and downsets at the same time as doing combinatorial commutative algebra and Grobner basis-like things to work with the monomial matrices. Okay, and topology, so this biparameter persistence of the wings. Don't think of the probability distributions, but of the wings. What we're really doing is persistent intersection homology. That's intersection homology where you sort of disallow interactions of vertices and edges, but we're doing it in a multi-scale kind of way, and it should be made precise that that's exactly what we're doing. Algebraic geometry, so this Kashiwara-Shapiro conjecture, it's a conjecture about the derived category of constructible sheaves given, so this gamma topology, which essentially says you have this, it's the same setup as the polyhedral partially ordered group setting, and it looks like this the Syzygy theorem is really a proof of their conjecture, which is lambda stratification of constructible sheaves. And in probability, what we'd really like to do is not calculate, if we have a data set of 1 trillion points, we don't want to calculate one simplicial complex on 1 trillion points. We'd rather calculate 1,000 simplicial complexes on a dozen points each, which is a much easier thing to do. But then you have to say in what sense the homology that you're getting from those dozen points 1,000 times is actually approximating the homology that you get from the original data set. And the point is it's very parallel. It's like a bootstrapping type thing to do. You're subsampling and computing with a whole bunch of subsamples. And it gives you only probabilistic answers, but the questions you were asking were probabilistic in the first place. So I could go into a lot of detail about that, but I won't because my time is up. So thank you for listening.
So for all the audience members, please go ahead and unmute yourself, and let's thank Ezra. And do we have any questions?
I have a question. So do you have any notion of stability for these persistence diagrams?
Who are you, by the way?
Oh, I'm Alex. I'm
okay.
Yeah, I'm at CSU. working with Amit.
Okay, all right, good to know. The stability for multi-parameter persistence. So the stability that we know so far is the one that I mentioned in the history slide. I don't know, where's the history slide? It's probably at about, oh, let's try that. That's close. So it's this stability, this rank function stability. So in general, if you want stability, you have to say what kind of input you're allowed. And so this is the kind of stability that's you allow. So multi-parameter persistence, sort of in general, there's going to be no stability because you have to say what the input means. So if you give yourself sort of continuous input, and then you do, then there's stability in the rank function, but there isn't and shouldn't be, in some sense, stability in the dimensions, because the dimensions can jump around a lot. So you have to define metrics. So then there's interleaving distances. So there's notions of what stability should mean, but in order to prove a theorem about stability, you need to have a class of modules that you're interested in first. And so people haven't. How do I say they in applications, people haven't identified enough applications with multi-parameter persistence to have a class of modules that they care about enough to prove stability. One of the things that we aim to do is to prove stability for the modules that come from Fly Wings. And what will probably help us there is that really there's kind of only finitely many places where the vertices can be, and sort of the Bezier curves, they're all semi-algebraic and they don't wiggle too much. And so they're sort of a nice class of modules. And so we should get some kind of stability there. And in fact, what we think is that what we're going to try to use is that they should all have somehow sort of a common fringe presentation, and that would provide the stability that you're kind of looking for. But it also depends on the distance that you're using. So we don't know which distance we'll be using. So it's kind of a complicated question. It's sort of, once you have an applied situation where you have a collection of modules that you're interested in and a distance that you're interested in using, then you want to prove a stability. But I don't know, sort of for real multi-parameter persistence, there is no universal distance and no universal class of modules that you'll want to be using.
Other questions? So I have a question. Ezra, there's this example in the Theory of Multidimensional Persistence paper by Gunnar and Afra, where I don't think this is their proof that multidimensional is in some sense not a discrete complete invariant, but it's an example illustrating this, where they have this two-dimensional filtered topological space where they start with two circles at the origin. Okay. Yeah. And then there's 4 places where things get glued on. So, right. Here we maybe glue on a cylinder, and here we glued on a punctured cross cap, which has 2 circles as its boundary. And here we glue on a different surface, and here we glue on a different surface. Okay. I guess now that I mention it, I guess this is very much a discrete multi-graded persistence module.
It is.
I was going to ask, how does this fit into your theory? But maybe the answer is it's from the start, I can't even make this a continuous, real. I
don't. So let me be clear. I don't actually care. So first of all, so a couple comments. First, call it multi-parameter persistence, because if you call it I know that they call it multi-dimensional persistence. But if you use multi-dimensional persistence, then when you say persistence in dimension 2, you don't know whether you're talking about the dimension of the homology or the dimension of the parameter space.
Sure. Yep.
In 2 parameters, then you can separate the parameters from the homology. Anyway, okay, that's just a comment. About this real versus integer, this theory, it works on an arbitrary poset, so it doesn't care whether the parameters are real or integer. So that fits perfectly well within this theory. So okay, you can write down fringe presentations of this thing and so on and so forth. Fringe presentations, the point is they have a matrix. Let me maybe share my screen again.
I see a matrix of all the different depths. I see.
Yeah, let's go to, I don't know, go to this, where did it go? matrix over here. This matrix over here, I mean, it's allowed to have scalars
we can't
in
see
it.
your, Ezra, we can't see your screen right now.
See my screen. I thought I did share my screen. This, now can you see it?
Yeah.
Okay, so this matrix over here is filled with scalars, just like the matrices in Carlson's Homology are filled with scalars. So you can still have continuous variation of these scalars, or maybe not continuous variation, but I mean, yes, you can have continuous variation. In the sense that there are moduli. When there are moduli, okay, variation can occur in two possible ways. It can occur because these scalars are changing, or it can occur because the upsets and downsets are moving.
Right.
I claim that when it occurs because the upsets and downsets are moving, that's a much easier case to analyze in statistics, and it happens a lot. What it's more so, okay, the Carlson's Homology observation about the moduli, about discrete invariants don't exist. While that's theoretically true, it's not necessarily an impediment to doing statistics with multiparameter persistence, because in your case, the variation might not be along the moduli space. In fact, I'm going to claim is almost never along the moduli space. Because how often are you going to get a data set where the point is that instead of gluing in a cross cap, you're gluing in a Klein bottle or something like that, right? Like, really, your data set, your data variation is such that in one data point you have a cross cap and in the other one you have a Klein bottle? I don't think so. It's more likely, as it is in our case, that when you're looking at these vertices and edges and things and you're moving them around in space, that the interaction of this vertex and that Bezier curve, when you move the vertex a little bit, it occurs at slightly different choices of the radius and thickness. That's true, but it's saying that this upset has moved. The coefficient that tells you that the interaction says that there's this upset and then there's a downset, so there's a birth and there's a death, the coefficient of that birth and death, it's a map between topological spaces, the coefficient is the same, it's just that you've moved the birth and the death a little bit. And what that's saying is the variation is not along the moduli space. It's just changing the moduli space entirely, because you're going from a module with one Hilbert function to a module with a different Hilbert function. And so it's not variation along the moduli space. You're changing something else about the modules. And it is, by the way, and I have this beef with actually the Carlson's Homologian paper. They immediately went to I'm going to put I'm going to stop sharing again, but they immediately went to discrete parameters. And then they said, when you have discrete parameters, there's no complete discrete invariant. Well, that's true, but discrete parameters is not what they started off saying. They said continuous parameters. And in continuous parameters, there's no discrete invariant because you have continuous parameters, right? So the barcode in one parameter is not a discrete invariant. It just isn't, because the endpoints can move continuously. And what I'm saying is that in multiparameter persistence, for the same reason, the continuous motion of the endpoints, we can deal with that statistically, right? And the fact that there's a priori theoretically variation that's continuous along the moduli space, that, my guess is, probably never happens in data. And even if it does happen in data, you're often doing it with Z2 coefficients. And so it's not actually continuous. The moduli spaces will be finite because the field is finite. And so you can still do statistical analysis using these things. The obstruction to discrete invariance that Carlson's Homologian put forward, it's true, it's theoretically there, but it will never happen in data, and you shouldn't let that stop you from doing data analysis with multiparameter persistence.
Very nice, that helps a lot. Are there questions for Ezra? If not, let's thank him again.